Yeah, so I want to talk to you today about Dorsum Zirkel and MareImbrium. Just real quick, this is a LROC oblique image of, so Dorsum Zirkel is right here, and some of the uplifted lava flows that I'll be talking about are right here, and they extend all the way into MareImbrium. Okay, so just real quick, for those of you who are not familiar with tectonics, so we're looking at a wrinkle ridge, and they are large compressional landforms found only within the lunar maria, and they are formed predominantly as a result of load-induced subsidence and flexure of the lunar lithosphere. So after the basalt emplacement in the maria, all that starts sinking down and forms those wrinkle ridges. And you can see the image on the left of how they're kind of wrinkly. And this other image, this cross section, wrinkle ridges typically have this broad arch with a ridge on top. And like I mentioned before, they're compressional landforms, so the reverse faults. How exactly those reverse faults manifest under the surface, we still don't particularly understand, and this is a cross-section from Waters 2022 paper trying to figure out exactly how those faults manifest under the surface. And this is also, people are trying to figure out how they manifest on the surface on Mars and Mercury as well. So, like I said, Dorsum Zirkel is located just about on the edge of MareImbrium. To give you some additional context, the Chang'e 3 landing site is right here, and then the Apollo 15 landing site is this blue triangle. And so to give you a kind of time scale, so MareImbrium formed about 3.9 billion years ago, and most of the basalts within MareImbrium erupted 3.6 to about 3.3 billion years ago. And this figure in the lower right shows that there are just hundreds of wrinkle ridges in Imbrium, but then also across all the Mare basins. And most of the ridges inside Imbrium are concentric around a mascon that's within MareImbrium. And this is the colors that you see in this image correlating to the Yu et al. 2017 paper, where they use the buffer crater count method to derive ages, the formation time for the wrinkle ridges. So if you're also not familiar with the buffer crater count technique, it's a really interesting method to where instead of defining an area and counting all the craters, this is actually specifically for linear features. So you essentially only include those craters that superpose said linear feature that you want to get an age for. And for the Yu et al. Work that they did, so they derived an age of about 3.1 for those ridges. Well, what's neat about Imbrium is that we have these younger flows. So one of them is called the Euler flows. There's also some a little bit south of the Euler manifesting from the Lambert area, but most of the flows that we're looking at that cross Dorsum Zirkel are from a source by Euler crater, which is located right here. So a Shaber paper from 1973 suggests that these young flows range in ages from 3.1 to 1 billion years. However, recently with Hiesing et al. 2011 suggests that one of those flows is probably Imbrium in age. These are high titanium basalts, and most scientists agree that there's a series of lava phases. So or it suggests that there's 3 phases of flows, so 2 early on and then 1 later. So again, what I meant, like I mentioned earlier, that the Euler area is the source site, and this site is a focal point of the horizontal extension stresses due to that base and loading. So essentially that's an area where the crust is opening up and it's allowing the series of crust penetrating dikes to bring up all that lava to the surface. So this is a really cool apollometric image. I'm pretty sure that many of you have seen probably one part of this image in a book or a manuscript of some sort, but this is a composite of 4 images. And to give you some context, so the Euler source region is down here. This is Mons Lahire right here, and then this is Dorsum Zirkel right here. And so you can see the lava flow fronts just kind of following on here. They do evade a kapuka here. They cross over a very subtle scarp that you can barely make out in this image. And then it keeps moving on towards the center of MareImbrium. So Brian in 1973 proposed that these flows occurred and essentially broke through the wrinkle ridges. And many papers published recently that are focusing on the lava flows, not essentially the wrinkle ridge, essentially agree with that. And so they kind of, roll with that statement. And so Brian had suggested that essentially the lava flow broke through here and pulled a little bit right here, but then pushed through over the wrinkle ridge, continuing on into the center of MareImbrium. So you can see some pulling right here, but to have lava pull and then also cut across a wrinkle ridge that is hundreds of meters high would be very difficult. And we don't entirely see any type of breakthrough right here. And this area is just uplifted. So Shaver et al. 1975 did a nice map of the different lava flows. And you can see in this map that they don't show that any of the flows evade or invade any of the wrinkle ridges. If anything, they pretty much cut across where the ridges manifest, essentially implying that these ridges were likely not there when those lava flows happened. This is the SLDM looking at Dorsum Zirkel. The circle area down here is that lava flow that evades the kapuka that I mentioned earlier. And the white arrows are pointing out the flow fronts for one of these flows. That pooling that I just mentioned is actually located right here. You can see a little bit of it. But when you look at the topography data, you don't see any type of breakthrough that the Brian paper was suggesting. So we're going to take a closer look right now of this white boxed area. So again, this is Kaguya image. We did look at this area with NAC, LROC NAC data, but you can't really, the flow fronts don't really manifest as well as looking at the Kaguya data. And so if we kind of follow along the arrows, so the yellow arrows point to the wrinkle ridge. So the wrinkle ridge kind of goes in a northwest southeast orientation where the flow fronts are moving in a northeast direction. And so the white arrows essentially point to those flow fronts. So you see that these flow fronts are obviously being uplifted. They are not altering the topography of those wrinkle ridges whatsoever. So in conclusion, we suggest that that Dorsum Zirkel did not exist during the emplacement of the Euler flows. So looking at modern data sets, doesn't show any type of embayments or any type of pulling. And like I just mentioned earlier, that the course of the flows is unaffected by Dorsum Zirkel whatsoever. And those flow fronts are only tens of meters in height, whereas Dorsum Zirkel is over 100 meters. And the Yu et al. 2017 paper getting the ages for the Wrinkle ridges is likely representing the average formation time, because they essentially digitized all the Wrinkle ridges and threw them all together and derived one age. So it's a good paper for a start, but it's now time for us to kind of break down those ages to resolve any type of diversity within the basin. So this is essentially what I want you to take away from this presentation, is that the formation of wrinkle ridges continued long after Mare emplacement. So they are not just done faulting. So